Hi, today I'll demonstrate for you a simple but important physics experiment known as Newton's bucket. You'll often see this discussed as a thought experiment in the context of Einstein's theory of general relativity and the so-called Mach's principle. But Isaac Newton first described it in 1687 as an actual experiment, which he carried out with a bit of rope and a bucket half filled with water. Here, I'm going to use an old LP turntable and a glass beaker. Warning: if you do this on top of your desk, there's a risk of getting your papers wet. I learned this the hard way. To run this experiment, I've taken an old LP turntable. I've disconnected the motor so that the metal disc can turn freely on its bearing. I also added some colorful stickers to make it easier to see the spinning in the video. The friction of the bearing on the turntable is low enough that it'll keep turning for a long time after I spin it up with my hand. The bucket is a 1-liter glass beaker filled about halfway up with tap water. To spin the bucket, I place it on top of the turntable using this wad of green Play-Doh to hold it in place. First, I put the wad of Play-Doh around the axis of the turntable. Then I place the beaker on top and adjust it so that the beaker is properly centered and upright. We don't want it to wobble too much and risk having it fly off and spray water and even broken glass all over the place. After the beaker is properly centered and upright and it looks like the Play-Doh will hold it in place, I spin up the turntable with my hand as fast as I can. You can see that the surface of the water in the beaker curves because of the centrifugal force. It can be shown mathematically that the surface of the water becomes a paraboloid. Notice that it takes a while for the water to pick up the full angular speed of the turntable, and you can see that the curvature of the water increases for a while after I stop spinning up the disc with my hand. Since I need to spin up the turntable pretty fast to get the water to curve appreciably, it's important to make sure that the beaker is properly centered on the turntable and also that it's upright. I learned this the hard way. So maybe it's a good idea to move this experiment out of the office and into the lab. So again, here's the beaker. Here's the turntable. And here's a bit of green Play-Doh to hold the beaker in place. What Newton thought was so important about this demo is that the water doesn't curve because of the rotation of the water relative to the bucket. This was contrary to the principles of Descartes, who thought that all of physics should be explained in terms of how bodies in contact move relative to one another. That this is not so is clear in this case because initially the bucket is spinning relative to the water, but the water is not curving much. Later, when the water has picked up the full rotational speed of the bucket, there's no relative rotation between the water and the bucket, but the surface of the water is very curved. If I stop the bucket, for a little while the water is still spinning relative to the bucket, and the surface is still curved. And finally, as the water comes to a stop, there's no relative motion between the bucket and the water, and now the surface of the water is flat. What Newton concluded from this was that the curvature of the water depends on the state of rotation of the water not with respect to its surroundings, but with respect to an absolute inertial frame of reference. From this, he argued that an absolute concept of space, as opposed to a purely relative one, is needed in order to formulate the mathematical laws of dynamics. In other words, dynamics can't be framed entirely in terms of the relative displacements of the objects that we're considering. This was controversial in Newton's day, and it remains controversial down to the present time. The Austrian physicist Ernst Mach pointed out that it looks like the water in Newton's bucket curves only when the distant stars are spinning around it. Mach took this to mean that Newton's absolute rest frame could be replaced by one in which the total distribution of mass in the universe has no net spin. Inertial forces, like the ones that cause the surface of the water to curve in the spinning bucket, would then be the result of the interactions among all of the masses in the universe. Mach said this in a book, The Science of Mechanics, first published in 1883, which the young Einstein read and took very seriously. I suspect that this has a lot to do with why Einstein referred to his work as the theory of relativity. But Einstein's mature physics still invokes an absolute inertial frame of reference, just like Newton did 2 centuries earlier. Mach's principle and Newton's bucket continue to be debated among theoretical physicists. I'd read about this many times, but when I had to teach classical mechanics, I thought it might be nice to demonstrate the experiment to my students. As you can see, it's not so hard to do. And that first time that I did this, I noticed that the curved surface of the water acts like a convex panoramic mirror, giving me a fisheye view of what's underneath the beaker. It's to make this a bit more visually interesting that I've added these stickers to the surface of the turntable. When I was a kid, you'd still see this kind of panoramic mirrors in shops, where it would help the owners to keep an eye on potential shoplifters. I guess that nowadays this is all done with digital cameras. So, there you have it, Newton's bucket, a simple experiment with a long and rich history in physics.
Entonces después hay que editar. Muy bien. Eso no había pasado nunca. Ok, bueno, vamos.